Hi everyone, it's me again. I'm Ian, I'm with Luis this time to talk about Space Robotics Challenge backstage. So in this talk, we're going to talk to you about some of the simulation components we created for this challenge and share some of the challenges we faced while running the competition. So a little bit of background about the Space Robotics Challenge. It's one of the NASA Space Robotics Centennial Challenges, and this challenge involves a R5 robot, which is also known as a Valkyrie, to perform various tasks on the surface of Mars. So there are 3 tasks, which we will show you throughout this presentation, and there are different checkpoints in each task. The unique aspect of this task is that the robot has to complete all the tasks in one go, compared to the challenges that we hosted in the past. For example, the DARPA Virtual Robotics Challenge, you have the walking, driving, and then manipulation, and everything is done separately in separate environments. And here, the real challenge here is to do them all at once. So teams are expected to do the tasks semi-autonomously or fully autonomous, which one team actually did, and they did well, too. And we also restrict network traffic to simulate communication delay between Earth and Mars, and also we added limited bandwidth. So at the end, there are 20 finalists, down from 93 teams after the qualifiers. So we're just gonna go straight to show you what it looks like. I don't know if you noticed, we're doing the simulation, the presentation, everything inside gazebo. So what you're seeing right now is a playback of one of the runs from the winning team coordinated. So what you're seeing here is the robot doing task 1, which is orienting a satellite dish. So just to give you an idea what the simulation looks like, so we have the RoboNaut 5 robot. It has multi-sense head, so it got cameras and spinning lidars. And we also use the controller provided by HMC, the whole body controller, and then we also provide a grasping controller. And these controllers are used by all the teams, so they have to use the same controllers to make the robot do its tasks. I'm going to zoom out a little bit. So what you're seeing there is just task 1 in the bottom section, and then there's task 2 in the middle section where they have to carry a solar panel and then deploy it somewhere here by the solar array and then plug in the cable. And then after that, they have to move in, climb the stairs, and then go into the habitat here on the top of the screen, and then they have to find and repair a leak, and that's task 3. We'll come back to the other task later. The competition is hosted on the cloud. We use CloudSim, a tool that was presented last year at ROSCon 2016. So basically, CloudSim is a tool for managing and provisioning machines on the cloud, specifically Amazon Web Services, AWS. So what you're seeing on the right is a screenshot of what the competitors sees. So this is the entry page that they go to, they log in, and then they get to launch what we call a constellation. And a constellation is just basically a group of machine instances. In this case, they launched 2 machines. So we have the simulator machine, which runs Gazebo, ROS Indigo, and also the SRC simulation package, which we developed. And then down the bottom, it also launched the field computer. This is where the team software is run. So you can also see there are buttons on the right. Once you launch the machines, you can click these buttons to start running the simulation. And once they're ready to perform the task, they can start their own software down the bottom. The new feature that we added for this particular challenge is the use of Docker. We find it great. It helps us to provide reproducible environment. We can do it locally and then deploy all the changes that we made onto the cloud quickly. So for example, you can start simulation in one instance in a container, kill it cleanly, and then start another one in the same instance. We also use it to deploy the team software. So they give us a URL pointing to their repo. It can be GitHub, Bitbucket, public or private. We'll go clone their repo and expected that there's a Docker file containing all the setup of their software. and then we'll build an image and run a container off that and deploy it on the cloud. The nice thing is that they can do whatever they want in the container, and we don't have to worry about it interfering with all the monitoring processes that we are running on the host machine. Just a summary of the different components in our architecture. So on the top right, we have the simulator instance running Gazebo, the SRC simulation package. It's always logging. After each run, we upload the logs to S3. So for example, what you're seeing here in the back presentation is just a log that we downloaded from S3. And on the left, we have the field computer. It's got the team software on it. And then we run what we call a traffic shaper, which just regulates traffic between the team's computer and the operator control unit. This is their local machine that are running and talking to their software on the cloud. So we add latency and limit bandwidth through this channel here. And then now I'm going to hand over to Luis, who will focus more on the simulation package that we developed.
Okay, so as Ian mentioned, let's talk a little bit about the simulation part of things that was developed specifically for this challenge. And to understand the software that was written to integrate the controls of the robot inside simulation, we have to talk a little bit about the software that is running on the real robot. So there are two main pieces of software. One is a hardware interface provided by NASA JSC, and the other one is a whole body controller maintained by IHMC. The controller builds on top of the hardware interface to provide a ROS interface that can be used to control the real physical robot. So in simulation, we want to use these same pieces, but we want to run the simulation inside the Gazebo simulator that we're seeing right here. And to make the bridge between these two, there are a lot of different ROS packages and nodes running, connecting all these bits and pieces to make sure that the code that the competitors are writing for the simulation can also work on the real robot and vice versa. So I'm not going to go into the details of how this integration worked. I'd like to focus on the software that was written specifically for this competition, and it's this little piece here in the corner. It's called SRC Sim. It stands for Space Robotics Challenge Simulation. And it's basically a bridge between, it provides an interface between the Gazebo simulation and what's going on there with the simulated robot and the competitors, and also Cloud Sim. So this piece is not necessary to simulate Valkyrie R5 inside Gazebo. It's only necessary if you want to run the competition itself. So some of the features of SRC Sim are, some of the things it provides are, first of all, the world mechanics. Ian showed you the satellite working before. That's an element of the world, the model, the way the satellite works, the fact that when you turn the wheel, the satellite also moves. All this is controlled by the SRC Sim package, controlling the world mechanics. The package also provides real-time scoring, so it keeps track of what the robot is doing and how many points it's scoring, and it also provides teams a way to restart or skip checkpoints, because since the competition had to be run all in a row, we gave teams, it was in the rules, the chance to skip a checkpoint they didn't want to complete to continue from there, or restart if the robot, for example, fell, or you dropped the tool on the floor and you couldn't get it. So the plugin controls the whole world and rearranges the objects and repositions the robot accordingly. The two last points are features that are not specifically on the SRC Sim package, but features that we added to Gazebo to make the challenge easier to implement. So one of them is a harness plugin, and that's basically a plugin that allows you to slowly lower a robot while its controllers are getting started until it touches the floor. And once the robot can stand by itself, you release the harness, kind of like a harness in the real world. And this has been released with Gazebo 7 and can be used for other robots besides R5. And another feature that we added was log filtering on while recording. So before this challenge, if you want to record a gazebo log, it would always record at 1,000 hertz with really high resolution. And when we are talking about this competition, there were simulations running for 14 hours, and the files were becoming huge. So we introduced this feature that you can filter as you're recording. So for the competition, we filtered at 40 hertz. And we decreased the resolution, and you can actually see this here in the log playback. Sometimes the limbs of the robot and the parts of the fingers kind of seem to be detaching from each other. It's not a simulation error, it's just that the log was filtered and the resolution was lowered. We had some problems also with the harness and the whole fact of being able to restart and skip a checkpoint and the robot teleporting in the world like this. The controller is great. It works on Earth, it works on Mars, but it doesn't support robots that can teleport yet. So that was a challenge that we faced and the teams faced during the competition, and people had to work around this limitation. Another feature of this package is a random world generator. This is a script we provided for teams so they could generate different worlds, valid worlds for the competition for practice. During the finals, each team had to compete with 5 different worlds that weren't known in advance. So it's really convenient to be able to practice with as many worlds as possible. So this script would randomize things like the configuration of objects in the world, their parameters, so for example, the friction on the wheel would change every time, or the position of the sun, and the targets. So the target of the direction you have to turn the satellite, or the target, like where is the leak inside the habitats that we're going to show you later. This was all randomized automatically by this script. And the script could also produce a full world valid for the competition with task 1, 2, and 3, or a world that has only one of these tasks. Even though the competition had to be competed in a full world, it was convenient for practice to have a world that has only one of the tasks. So here on the left, we can see many different worlds that were generated for task 1, which is the satellite task, with various valid configurations. And on the right, we have many worlds generated for task 2, which is the solar panel task that Ian will show later. And they are all also valid worlds for practice. So let's skip task 2 for a bit, and let's go to task 3, take a look at how that works. As Ian mentioned, it starts by going up the stairs, and then Valkyrie opens that door there by turning the wheel, and has to push the door and enter the habitat. Once Valkyrie gets inside the habitat, she sees this table, which has 2 tools on top of it. One of these tools can find leaks inside the habitat, and the other tool can fix leaks. These tools were not modeled after real tools that exist in the real world, so we could be a little bit creative the way that we were implementing them in Gazebo. So it's fun to mention because people are always like trying to implement different things in Gazebo, and it's hard to imagine that sometimes you can implement one thing with something that is completely unrelated. The leak detector, for example, we implemented it as a logical camera, which is a new sensor that we added on Gazebo 7. And basically what this sensor is doing is detecting whether the leak is inside this frustum there that is delimited by white lines. And we can see the white lines, but the robot actually cannot see that frustum. So the robot will have to wave this around the wall until it finds the leak. So while the robot is doing that, let's talk a little bit about all the different checkpoints in this competition. There are 18 checkpoints in total, and many of them had very specific logic that we had to implement just for this competition. The leak detector is one of them, and we wrote very custom code just for it. But there are other types of checkpoints that they had a lot in common, so we thought we should make a common solution for them and package them into Gazebo so other people can write them. It's not very complicated code, but it's code that probably a lot of people are needing for many use cases, and they are rewriting over and over again. So we're just making this available with Gazebo. One of them is the box plugin, which was used in 7 checkpoints. Basically, what this plugin does is it checks when a certain object reached a certain box region in the world. So this was used, for example, when the robot would reach a certain area, a certain checkpoint, we would check that. And that communication is done via gazebo transport and then translated to ROS for the competition. Another plugin that was used for 4 different checkpoints is the touch plugin, and it checks when 2 specific objects are touching each other for a continuous time exclusively. So this was used to check when Val had successfully picked up a tool or the solar panel or other things like this. The touch plugin is already released with Gazebo 7, and the box plugin will be ported to Gazebo 8, probably using ignition transport. So just to wrap up task 3 here, this is the moment when the Valkyrie, like the winning team, finally found the leak, and they are getting ready to press the leak patch tool against the leak to fix it. It has to be pressed for 5 seconds for the checkpoint to be completed. This was actually the only team that was able to complete this checkpoint. So it's very exciting that someone actually did it. And now I'm going to pass it to Ian, who's going to talk a little bit about the challenges we had.
All right, thanks, Luis. So we implemented a lot of stuff behind the scene, and we also faced a lot of challenges along the way. And today I'm just going to share with you 2, one technical challenge and one non-technical challenge. So one of the first is simulation stability and performance. There's always a trade-off between having a very stable simulation, physics simulation, and real-time performance. So after the first pass of integrating the IGMC controller and making Valkyrie, or R5 robot, walk, we arrived at roughly 0.10 real-time factor. That's 1/10 of the speed of real world. So each team per run is allowed up to 3.5 hours simulation time, so which works out to be 35-hour real time for 1 run. And there are 5 runs to do. So if a team decides to use up all the time available to them and do all the runs one by one, you end up with, you probably have to spend 7.3 days just to do the competition, assuming you don't sleep. So you can see that improving performance has really been a high priority in the weeks leading up to the challenge. So some of the suggestions that we're going to offer here that we actually did, and some of them we did not, but hopefully that will help you with your simulation projects. So we use simple shapes for collisions. So these are boxes, spheres, cylinders. These has become a standard procedure for us when we're creating simulations. They generate better than meshes and which produce unstable contacts. And then we started doing things like inserting models and deleting them between checkpoints. So a good example is when the robot enters the habitat. Before the robot enters the habitat, there is actually nothing in there. And once the robot enters, we spawn the repair tool, the leak detector tool, and then we deleted everything outside of the habitat. So that helped a bit. And then we also experimented things like relaxing the ODE physics solver parameters. This is the forked ODE that we have in Gazebo. So we bumped up to 2 millisecond step size. The original default value is 1 millisecond. So this is the step size, which is the time you advance the simulation by every update. So the simulation we effectively run at 500 hertz, which is what the IHMC controller needs. And then what we did is also reduce iteration, so we're sacrificing simulation accuracy for speed. But however, we did not merge these changes. It was very close to merging until the team reported that there was a test failure in their overnight testing. So if we had time in the future, I think we could have done better. We also tried different physics engines. There are 4, ODE, Bullet, SimBody, and Dart. We could have played around with others. And the last challenge I want to mention is there's always a challenge for us to determine whether or not a task can be solved. So it's best illustrated by looking at task 2, which is when the robot has to grab a cable and plug it into a solar panel. So we got requests to change the weight of the solar panel, the color of the solar panel, which we did. And then we also got requests to change the position of the cable and stuff, but which we did not do. But there's always the question, like, whether or not we're making the task too easy for them or not. So just an example, we made the change to change the cable geometry, but making it a little bit elevated from the tabletop so that it's easier to reach under and grab. So once we made that change, other teams complained because we have just broken their object recognition model that they trained for the old cable geometry. So I guess the lesson learned there is that we should be more active about collecting feedback from teams at regular intervals. So we're getting a lot of feedback in our issue tracker. The teams are not afraid to tell us how the changes we made have screwed up their code. But what's equally important is that they tell us what's working, so that information is missing. And finally, this is just showing the robot walking to the final checkpoint. So team coordinator is the only team that got perfect score, and then this is just showing them walking to the last checkpoint. And that's all. I'd like to thank everyone involved for making this competition possible. Thank you.
Thank you, Ian and Luis. I think we have time for one quick question. Juan, can you get set up? So anyone got a question? Come on up to the microphone.
These are some bloopers, by the way, that we're playing.
Hi. Sorry, I have a background in RoboCup at work and at home and industrial. And there's always these ref boxes. And every year they change the rule book a little bit. And if you're the maintainer of the ref box, you have to like change the automated generation and all this. How extensible is the task generation? And like, if they change the tasks and add new tasks, how much more code do you need to write to, I don't know, continue? Is it all auto-generated and you have some nice feature, so you say, okay, give me a task that does this and this, and...
Oh, you're talking about the random roll generator?
The random roll generator, but it sounds like you're doing automated marking or automated grading of the tasks. Or
Oh, yeah. So each checkpoint has an objective, and we are checking that objective on the fly.
Yeah.
So some of them are very common, and like if you have checkpoints that are like about things reaching a certain region, you can reuse our code, or like some robot picking something up, you can reuse our code. But if you have a more custom checkpoint, then you're probably going to have to write some logic there.
Okay, so it was just those three checkpoints that you...
Yeah, so like there are three main categories. One is the region checkpoint, the other one is the like picking things up, and like the other one is actually custom, so there are 7 different checkpoints there that are very custom, like for example pressing the leak against the leak patch tool against the leak is a very custom checkpoint for that case, because you have to press the button at the same time, so it's a lot of little things to check.
Okay, yeah.
Okay.
Thanks.
Let's thank Ian and Luis once more.